Hello, welcome to my channel. In today's video, I will discuss about my BMS project intended for DIY makers. Want to learn about power management, battery management system, and designing PCBs for power application. I'm using the EasyEDA schematic capture and PCB design. It's a very simple tool. It's easy to learn and also have uh, flexibility or power to develop high performance PCB design. The BMS module uses the BQ76920 from Texas Instrument. It's a fully integrated BMS controller, have a 5S configuration with implementing a passive cell voltage balancing, have current sensing for overload, short circuit, and monitoring. It also have a charge and discharge switching control for protection and uses I2C interface for communicating to external MCU. In this design, I'm using the Atmega 328P for Arduino compatibility. I will discuss individual subsystems and also some design guidelines for PCB design, thermal consideration, noise considerations, and component placement. We can discuss the cell voltage sensing. So individual cell will be monitored by the BMS controller before it connects to the ADC or the analog to digital controller. It must pass through a low pass filter. So R31 and C19 are the low pass filter components. This will remove or eliminate noise coming from the battery wiring system or cell wiring system. If the load connected across the battery pack is noisy and the connection of this cable assembly is quite long, then it will noise will interfere with this sense signal. So R31 and C19 will eliminate the noise or reduce the noise so that it will not interfere with the measurement. And this component should be located very close to the MC to the BMS controller so that it will improve the noise immunity of the system or reduce the noise interference in the BMS data. The next section is the passive balancing. The passive balancing will be implemented individually to each of the cells. So the passive balancing system is controlled by R31, Q1, and R100 and D10. R1 will limit the amount of power or current, and Q1 will provide the switching of R1 across the cell, and R100 will accept the drive signal coming from the BMS controller. The consideration for Q1 is since the switching is a low voltage switching, which is maximum of 4.2 volts, so Q1 should be selected as a low BGS MOSFET. So D10 is important to limit the or to clamp the voltage between the gate to source of the MOSFET, because this MOSFET is a low BGS MOSFET. So any switching between cells or might generate a voltage spike on the gate of the MOSFET. So the MOSFET should be protected by the Zener diode to avoid the voltage spike or clump the voltage spike from the gate. So individual cells will have its own balancing circuit here. Similarly for the low pass filter. The cell sensing is connected to a header connector and going to each of the individual cells. The lowest one is the B minus, or the lowest possible voltage of the first cell. So it's connected to it will become the B minus. Then this component here, it's a ground tie. It means it just create a separate grounding for power. So B minus is the main power bus. Then G and D is the signal grounding or controller grounding. So this 0R or jumper will isolate these two grounding together, because connecting all the grounds together, the power and the controller ground, it will generate some noise interference. So ground joints or ground tie will be needed to isolate the two grounds together in the PCB design. The battery module is power connection is using the XT30 connector together with the battery pack connection. The next one is the boot up. So SW1 will be connected to cell number 1 to provide the drive voltage for initial startup. So switch 1 will momentarily turn on and drive D3, and also through R32 will drive the BMS controller. The BMS controller start up or boot ups and try to do some self-testing and monitoring. If everything's okay, then it will start up. It generates some regulator output voltage. Then the SW1 will also provide a boot up for the MCU power system. So MCU will have its own power switching or power supply, and it will be controlled by initially by the SW1. So BMS and MCU will boot up almost at the same time. The next one is the current sensing. So R38, 18, and 19 is a current shunt sensor. This component is to be determined. It depends on the maximum current that will be used in the design. So I will modify this to match my application. In this design, I'm planning to have at least 30 amps of discharge and charge current. So the sensing signal from the shunt will be connected to R16 and R17 together with this capacitor, forming a low pass filter. Since the voltage across this shunt is very low, it's very important that the noise will be reduced or eliminated before it can go to the analog or shunt amplifier inside the BMS controller. The next section is the protection switches. So the controller have separate discharge and charge switching protection. So I'm using 4 power MOSFET connected in parallel. Since connection of the MOSFET in parallel, they should share almost similar current. So it's good to use some gate resistor for each of the individual cell to have better balancing on the current, and at the same time it also reduces the capacitive ringing during turn on and turn off of the gate signal. So similarly for the charge switch, it also uses four MOSFETs, so charge and discharge will have the same current capacity or current rating. The gate drive for the charge is a little different because of the requirements from Texas Instrument as the controller. The main consideration for the difference of the gate driving is the charge MOSFET, the ground, once the MOSFET turns off, the ground, the P ground will become floating, and once it's floating, there's a probability that it will generate some voltage spike. It's either positive or negative, so there's a protection circuit here comprising of Q12, D2, and D1 to avoid or reduce the effect of the voltage spike during turn on and turn off of the MOSFET. So that is the main protection circuit. So the P ground here will be connected to the battery pack connector here. So this one is the P ground connected to the load, and this one connected to the battery pack. And this one will be B minus, and the other side is the P ground. The next one is the I2C. The I2C interface for the BQ76920 is a 3.3 volts. So we will be using a voltage translator. I'm using the PCA 9306 to translate the 3.3 I2C signal to the I2C 5 volt signal because the MCU uses a 5 volts power supply. Also, the alert signal coming from the BMS will be translated to 5 volt signal as well. This connector here is for the connection for the NTC temperature sensor. It will have two, one for dedicated for BMS protection and another one for Arduino. So the Arduino will provide the secondary protection for the temperature. Okay, that is the main battery management system. We can go to the Arduino or the MCU controller. As discussed in the previous uh, page of the BMS controller, the switch one will boot the power supply of the MCU as well. So MCU boot will provide the drive signal to D4 and turn on the Q20. The Q20 will drive the Q17 because Q17 is a P-type, and once a P-type MOSFET, if the gate is grounded or negative to the source, it will turn on. So once Q20 turns on, the Q17 the Q17 gate will be almost connected to ground, and Q17 will turn on. Once Q17 turns on, then it will be provide power to the LDO or voltage regulator here. Then it will generate the 5 volt supply of the MCU. Once the MCU is powered, it will do the initialization, power up, and also startup sequence and to check if everything is okay, hardware. And at the same time, it will also check the connect interface to the BMS. Once everything is okay, then it will provide a enable high signal to this pin, and this power supply circuit here will latch up. So the SW1 on the BMS side should be pressed for some time before everything initialized, then everything is okay, then the MCU will latch up, then it will continuously power the system. In case there's a failure on the hardware and the MCU detected the data coming from the BMS have problem or some hardware problem detection in the MCU, then the MCU will provide a low signal to this pin, and by the delay of this component here, then it will turn off Q20. And at the same time, once this one is turned off, then the gate of this MOSFET will pull to high, then it will turn off. Then it will power up or power down all the system, which eliminating any discharge of the battery. So the connection of the MCU is similar to Arduino Nano, and some of the connection here are not implemented in the design. It will be used for future project. I'm thinking about active cell balancing for very high capacity battery system. Here is the connection of the I2C, and the MCU will also communicate with UART to USB. So I'm using the CH340 controller. So that is the MCU side of the BMS controller. Next is the BMS PCB. Here is the BMS PCB. The power section is almost done. So here are the charging MOSFETs and discharging MOSFETs. The consideration for this is really for the thermal and the maximum current handling capability. So I'm using a power via to improve the handling capability of the MOSFETs. So the power bias will help in reducing the resistance of the PCB copper connection, and at the same time it will reduce the temperature of the MOSFETs terminals. I'm planning to have at least 30 amps of maximum current, but I have also an option that I will place a heatsink above the MOSFET assembly and a screw point on the bottom side to hold the heatsink together with the MOSFET so that it can handle higher current, probably at least 40 amps. Here is the current shunt. The current shunt will handle most of the current. So all the current coming from the MOSFET will pass through the current shunt. So I added more power bias, and at the same time also have the solder mask to expose the copper area, and I can place a solder lead to these connections to improve the temperature and improve the current carrying capacity of the PCB. So here is the battery module connection. Here is the connection to the load for discharge. Here is the connector for the battery sensing, the connection for the two temperature sensors for the BMS and MCU. This section is the power supply switching and voltage regulator at Mega 328P, UART to USB, and the BMS controller here. Here is the boot switch and USB interface. And here is the balancing systems. So the consideration here is the balancing connection should be the connection should use a higher or bigger copper trace so that because the balancing and the voltage monitoring circuit uses the same terminal of the battery. So uh, reducing the resistance of this connection will improve, will not affect the measurement accuracy of the battery voltage. So that is one of the consideration here. And at the same time, the connection here have more current compared to other uh, BMS input connections. So in this design, we really need to consider the component placement. The, the priority is the analog filter or sense filter. It should be connected very close to the terminal of the BMS controller to avoid the noise interference. Also, we need to provide a ground loop or grounding plane. It will grounding plane for analog section and grounding plane for the digital section because the digital section through the USB communication interface and the I2C will generate a lot of noise. So we need to isolate the two grounds. Then the two grounds will be connected to the lowest possible voltage, which is the B minus. And another consideration is how we can create the grounding plane. Individually, we can place a via for each of the individual grounding, so we can mark all the grounding here. So in the digital ground, I'm using the C ground. Then each of the C ground point will have at least several grounding vias and connected to the ground plane. This will significantly reduce the impedance of the ground loop, especially on the MCU sides here and the BMS sides. We can add more ground BS if needed. The good thing for this EasyEDA design is once there is a problem, it will mark automatically and we can easily see if there's a problem with the PCB design. Okay. Another consideration is during the layout, we can connect the shortest possible connection first and optimize later on which areas need to consider for noise immunity and power and temperature. As here, this one is the power switch and it will dissipate some power, so need to have some copper area or copper plane. And at the same time, for the LDO, will also dissipate some heat, so it will have a ground plane and the power plane. So the placement of the component is very important in the initial stage of the design. So building the concept first and try to do the placement before starting to do the layout so that you can easily view how the layout will proceed or you can anticipate possible problem in the layout later on. Okay, that's all for this video. So I will continue working on this design and hopefully I can finish it within several days and upload another video. If you need some If you want to learn more about designing PCB using EasyEDA, I'm conducting a one-to-one tutorial for the EasyEDA PCB design and also uh, tutorial for battery management system and power system design. So if you are interested, just let me know. Okay, thank you for watching and see you next time for another video.